My name is Dawn Mesner, and I'll be talking about the differential drag implementation and lessons learned for the CAT mission. First, I'll provide a brief description of the CAT mission. Then I'll discuss differential drag and how we model and implement drag maneuvers on CAT. Next, I'll go over some results from deployment and operations. And finally, I'll discuss how we updated our drag maneuver planning process based on our operations experience so far. The CAT mission consists of two identical 3U CubeSats, each with an industry-provided RF payload. And you can see here that each spacecraft has two deployed solar panels, an S-band antenna on the positive z-axis, and a GPS on the negative z-axis. The spacecraft were deployed from the International Space Station on January 31st, 2019. And you can see in this picture the two spacecraft immediately after deploying from the NanoRacks module. The spacecraft used differential drag to maintain in-track separation distances between 10 and 150 kilometers, with the CAT-2 spacecraft always remaining behind the CAT-1 spacecraft. Shown here are the attitude modes that we use for differential drag operations. You can see that the maximum drag has the x-axis pointed along the velocity vector, while the medium drag attitude has the y-axis pointed along the velocity vector, and the minimum drag attitude will point the negative z-axis along the velocity vector. This provides a max to min drag area ratio of 12:1, or a max to medium drag area ratio of 3:1. And drag maneuvering only occurs during eclipse, so as not to interfere with power. Prior to launch, we chose various modeling and simulation tools. For orbit determination, filtered position and time states from GPS telemetry would be input as measurements to a Kalman filter in ODTK. Then STK and astrogator would be used for trajectory propagation and for targeting the differential drag maneuvers. So to accomplish this, it was necessary to develop plugins for both ODTK and STK that calculated the drag cross-sectional area based on the spacecraft's attitude. So utilizing a simple flat plate model for the spacecraft, the projected area of each plate along this Earth-centered, Earth-fixed relative velocity vector direction was calculated. And because of the solar panels, there would be instances where one plate blocked another. And in that case, this shaded area was also calculated and accounted for in the drag calculation. Next, I'll go over how we initially planned drag maneuvers. After deployment, the spacecraft are separating with CAT-1 ahead of CAT-2, and nominally the spacecraft are sun-pointed while in sunlight and in minimum drag mode while in eclipse, so as to prolong lifetime. Initially, max drag maneuvers are needed on CAT-2 in order to counteract the deployment acceleration, and if necessary, bring the spacecraft back below 150 kilometers. After that, the separation is maintained between that 10 and 150 kilometers. We selected a target separation distance of 75 kilometers and a 0 kilometer per day target separation rate. And each week, the latest spacecraft state is propagated forward and drag maneuvers are added as needed. So for example, if the spacecraft are too close and continuing to close, CAT-1 would have a max drag maneuver added to it. Then once the spacecraft reached the target separation of 75 kilometers after 1 to 2 weeks, they're still separating, and so a max drag maneuver is added on Cat 2. And once this spacecraft separation is halted and they're at their target separation and the target separation rate, both of the cats are returned to the nominal minimum drag attitude. These drag maneuver calculated times and quaternions are input into the CAT app, which coordinates and updates all of our spacecraft commanding and then outputs the daily command loads for the spacecraft. So I mentioned we deployed on January 31st. We deployed at 10:35 UTC, and our first pass wasn't until 1834 UTC, but both spacecraft beacons were successfully detected during this first pass. Unfortunately, neither GPS on the spacecraft was able to track enough satellites for a good solution. And so the JSPOC TLE states were used for OD. We did change the nominal eclipse attitude to point the GPS to zenith in the hopes of remedying this issue. And after 6 days, Cat 2 did provide valid GPS solutions from that time through July of 2019. However, after July, the GPS solutions became invalid again, and we had to use TLE states for OD after that. For Cat 1, we've had to use TLE states since launch. So you can see in this plot on the right, the orange box represents the desired separation limits for the spacecraft, and the blue line is the TLE states for the first 6 weeks after deployment. You can see that differential drag began on February 13th. This delay was due to having to diagnose an attitude commanding error. But once differential drag was started, it only took 10 days to reduce the separation rate from 11.6 kilometers per day down to 0 kilometers per day. On March 14th, the spacecraft checkout and payload commissioning were completed. And on March 21st, the payload began primary operations. And you can see that the spacecraft was well within the desired separation limits when that began. So now I'll discuss moving into the formation maintenance now that the initial velocity after deployment was counteracted. You can see here that the spacecraft, both of them have spent a fairly significant amount of time in safe mode, and both of them have spent about the same amount of time in safe mode. However, Cat 1 has had to perform more maximum drag maneuvers during its lifetime than Cat 2 has so far. This indicates a slight closing trend that our modeling hasn't been accounting for. So we soon found out after deployment that weekly updates to the drag maneuver planning were not sufficient. These safe modes and command lockouts could quickly affect the spacecraft separation rate. And if a demotion happened to cancel scheduled drag maneuvers, that would just exacerbate the issue. So we worked with mission ops to create a process for manually adding drag maneuver commands to the loads. And initially, we only used that as needed. However, in September, we began regularly checking the separation trend midweek and more aggressively using these manual commands. Also in December of 2019, we raised that target separation distance from 75 kilometers to 95 kilometers. And reasons for both of those decisions I'll go over in the next plot. So here you can see that In August of 2019, we had a series of safe modes and command lockouts on both spacecraft, and they exceeded the desired separation before we were able to get enough drag commands in and recover the spacecraft. So it was after this experience that we began regularly adding those manual commands midweek and being more aggressive. Then in November, another series of safe modes and lockouts led to the spacecraft coming within 20 kilometers of each other before we were able to turn the separation rate around. And it was after this that we decided to increase the targeted separation from 75 to 95 kilometers in order to provide more recovery time in the event of a similar situation happening again. In February, we decided to make some updates to our drag maneuver planning process. Based on previous experience, we wanted to increase the frequency and responsiveness of the planning process. We now propagate the latest TLE forward to calculate the current separation and separation rate. And the desired separation is set at 95 kilometers, and the desired separation rate is calculated to bring the spacecraft back to that 95 kilometers over 3 weeks' time. If the current separation rate exceeds the acceptability bounds on the desired separation rate, then the required duration of differential drag maneuvering is calculated and added manually to the next available command load. This drag maneuver planning currently occurs twice a week on Mondays and Thursdays. And these process updates have also significantly reduced the amount of time required for planning each week. We plan to reduce that time even further by integrating the new process directly into the CAT app planning and command generation tool. In conclusion, the CAT mission has overall successfully used differential drag to maintain in-track separation distances between the two spacecraft. The in-track separation has never exceeded the lower bound of 10 kilometers, and the upper bound of 150 kilometers was only crossed twice. Based on our lessons learned, the MD-NAV team recently implemented more frequent drag maneuver updates as well as faster drag maneuver planning. And now that the primary mission is complete, we look forward to another year of extended operations. Finally, I'd like to thank our U.S. government sponsor, Wenjong Sheyong, my co-author on the paper, and the other members of the CAT, MD-NAV, and Mission Operations team. Thank you.